Hello everyone and welcome back to Intro to Python here on Cybrary On Demand. I am your instructor as always, Joe Perry, and today we're going to begin Lesson 1, Programming Basics Logic. In this lesson we're going to learn about Boolean logic and logical operations. Those operations are going to be and, or, and not. And then we're going to learn to implement those logical operations in part 2 by learning about the logical laws and the derived operations. Most specifically, XOR is going to be the one that we really focus on. So what is Boolean logic? I've used that term in a couple of these videos already, and it's important to understand sort of what it is and where it comes from. So Boolean logic was published by a man named George Boole in the book The Mathematical Analysis of Logic, which is a page-turner, I assure you. It's not. It's an incredibly dry and extremely boring book. It was published in 1847, and like most old things, it's terrible. That was mean to say, but I'm going to stick to it. Stick to my guns, right? More seriously, though, it was influenced by a Sanskrit philologist, Panini. I think that's how you pronounce that name, but honestly, my Sanskrit is rusty. I haven't taken it since high school. You know how it goes. Panini was a philologist is a person who is a grammarian. They study the evolution and the design of languages and grammar and how they function. And he was quite possibly the first person to apply formal logic to the concepts of linguistics and grammar. And over the course of creating that work, and over the course of sort of documenting that, Panini developed the concepts of sort of truth and falsehood that were then adopted to create Boolean algebra and Boolean logic. So there are only two values in Boolean logic. It's not like normal math where there's, an infinite number of numbers and arrays and things like that. In Boolean algebra and Boolean logic, there are only two possible values, 1 and 0. And then there are only three possible operations. There's AND, which is represented in formal logic by a period, and usually in shorthand or informal or programming, it's represented by an ampersand. There's OR, which is represented by the plus sign or by the pipe. That's the straight line kind of up and down. Usually it's going to be on the same place as your forward slash. And then NOT, which is usually represented by a tilde. So those are the only two values and the only three fundamental operations of Boolean logic. But from those very simple concepts, we're actually able to derive all of math, all of modern computer science, all Turing-complete machines, and a pretty substantial chunk of mathematics. Now, there is, for those of you who are really excited about the most modern technology, quantum computing does kind of play with that a little bit and introduces relativistic and probabilistic states. But fortunately, this is an intro to Python video and not a quantum computing video. So save your hate mail for when I earn it later. So in this lesson, we're going to spend a lot of time on truth tables. And if you've never had the joy of going through a CS 101 class, a truth table is exactly what you see in front of you. It's a table of some number of values and statements, which is used to represent every possible state of the equation. So you have, in this case, we have two inputs, A and B, and you'll see those used pretty often. And with A and B, we represent every possible combination of those two Boolean factors or Boolean values, true or false. So A, by the way, in computer science, when I talk about true and false, that's the ones and the zeros of binary. Binary is an implementation of that Boolean logic. So we're going to use 1 and 0 instead of true and false in most of these places. Don't let that trip you up too much. So here you can see we have two 1s and two 0s under A. If we just had A in this table, it would just be two lines of 1 and 0. But because we have two factors, we have to represent every possible combination. And for those of you who know binary and understand how to read binary, you know that with two digits, you're capable of representing four numbers, 0, 1, 2, and 3. And a useful sort of equation when you're building your truth tables is however many inputs you have, it'll be that power of 2 number of rows, which is to say, well, that power of 2 number of possible combinations, so that many rows. Which is to say, for example, if you have 3 inputs, it's going to be 8. If you have 4, it'll be 16. If you have 5, it'll be 32, sort of on and on and on and on. If you have 5 inputs, I generally don't recommend building a single truth table. We're not going to deal with any truth tables larger than 3 inputs and 2 or 3 statements at a time. Your statement is going to have the same number of rows as your inputs, and that's just going to be whatever equation you're doing. And we'll see that. It'll make a little more sense, I think, in the next couple of slides. We'll kind of see that play out. But your statement is going to be just all of the solutions with those inputs. So as an example here, we have the first logical operation. We see that we have true and false represented with A and B the same way we do in this previous slide with 1s and 0s. And we see that AND evaluates to true, that is AND evaluates to 1, if and only if, so only in the case that all of its input values are also true or 1. So on this table, you can see that on our first row, A is 1 and B is 1. So that's representing the binary number 3. The AND, A and B, we're going to represent here, is 1. Because of the fact that both of the inputs were true, the output of AND is true. Pretty straightforward. The next row, we have A is 1, which helps us to evaluate this, but B is 0. Now, I'll say again, AND evaluates to true only in the case that all input values are true, which means that with B being 0, A and B is also 0. As you can see on the next row, A is 0, B is 1, still have a 0 in it, and on the final one, of course, both of them are 0, therefore AND is 0. A useful shorthand is that generally speaking, if you AND all of your inputs together in a truth table, you're generally only ever going to have one row evaluate to true. It's not 100% the case. There are complex inputs that can mess with that, but as a basic rule, you can generally trust that. So and I want to mention real fast, I always skipped it. AND is often referred to as the logical conjunction in formal logic classes. So if you hear that, that's what that's referencing. Now logical disjunction. OR is similar to AND in that it evaluates to true based on whether or not an input is true. It's different in the sense that if any of the inputs to OR are true, OR will evaluate to true. So sort of not exactly the inverse of AND, but to some extent it kind of feels that way, and it kind of looks that way on the truth table as well. For example, on our first row we have A and B both equaling 1. Now, it doesn't matter if both of them are true, so long as one of them is true, so A or B evaluates to true. On the next row we see that A is 1 and B is 0. Now with AND, you'll remember that evaluated to 0 because one of the inputs was false. However, because one of the inputs is true for OR, it evaluates to true. The next row, same thing with B being true instead of A, and then the final row, because none of its inputs are true, OR will evaluate to false. The third and final fundamental logical operation of Boolean logic is NOT, or the logical inversion. NOT evaluates to true if and only in the case that its input is false. NAND is generally used for single inputs, or it is used for the result of an equation. So for example, you can see here that I have NAND and NOR, which are two very commonly used gates in logic. Gates and operations are differentiated in that a gate is something that is actually physically constructible. So even though the AND, OR, and NOT are the fundamental operations, NAND and XOR are the two most commonly used fundamental gates, physical gates of logic. Don't get wrapped around the axle with that. You aren't going to need to learn how to create a circuit board or a circuit diagram. Don't worry about that at all in this class. Point is, NAND and NOR are two very commonly used logical operations which are derived from the three fundamental. So here you can see that NAND, which is not AND, is going to be evaluated based on the input from AND. So AND we already established is going to be 1, 0, 0, 0. NAND is just the logical inversion of that. So we have 0, 1, 1, and 1. Very straightforward, very kind of easy to wrap your head around once you've seen it a couple of times. A or B, you can probably guess because it's 1, 1, 1, 0, and NOR is the logical inversion of that. We're going to have 0, 0, 0, and 1. So at the next lesson, we're going to do some math. We're going to jump in and really start learning about some computational logic. We're going to learn about some fundamental laws of logic. Here I've included a comic from the inimitable XKCD. There are going to be a lot of XKCDs throughout this course because Randall Munroe is frankly a genius who has made the world a better place. That said, before we go on to the next lesson, we're going to take a second, we're going to do a knowledge check. We're going to break these videos up a little, or the next part of this lesson, we're going to break these videos up a little bit just so you have time to digest it and make sure you've learned the actual material. So which operation is the logical inversion of AND? What is derived from the combination of and NOT? The answer is NAND. What are the two possible values of Boolean logic? There are only two. True and false. What are the three fundamental operations of Boolean logic? There are lots of possible operations. There are only three that are fundamental. AND, logical conjunction, OR, logical disjunction, and NOT, logical inversion. So summary, in this video we covered basically what you just checked out on that last slide, the two possible values, the three possible operations, and discuss some of the derivations from those. Again, in the next video we're going to come back, we're going to learn about the laws of logic, and we're going to apply them. Until then, I am as always thrilled to have you here and hope to see you back on our next video. I'm your instructor Joe Perry, and this has been Intro to Python.